In this presentation, we're going to start to discuss magnetism, and specifically we're going to talk about simple magnets and magnetic materials. So it turns out that electricity and magnetism are actually related to one another, but this phenomenon wasn't really known until about the mid-1800s. But there were some hints that maybe they were connected. So for example, when we talk about electricity, we have positive and negative charge, and we know that like charges repel one another and unlike charges attract one another. Well, similar to electricity, magnets don't have charge, but they have poles. And so magnets have a north and a south pole, and then similar to electricity, if you have like poles, they repel one another, and unlike poles attract one another. So as a kid, if you ever played with magnets, you know that you can bring two magnets next to one another and they can pull towards one another without even having to touch one another, right? So they can exert force at a distance. And remember, anytime you have force at a distance, we associate what's called a field with that, like the gravitational field and the electric field. So we're also going to have something called magnetic fields, where force from magnets exerting force at a distance creates this magnetic field. So there's different classifications of materials in terms of magnets. We have permanent magnets, and permanent magnets basically have a north and a south pole, and it's permanently there, right? So those permanent magnets can actually create their own magnetic fields. They can exert forces on other permanent magnets. And they're made of a hard ferromagnetic material, and we'll talk a little bit more about what ferromagnetic materials are. But basically, ferromagnetic materials, some examples of them would be iron, nickel, cobalt, and there's actually a mineral called a lodestone that's a permanent, it's a ferromagnetic material that you can make a permanent magnet out of. There's also temporary magnets, and temporary magnets actually behave like a permanent magnet, but only in the presence of a magnetic field, or only temporarily. So, for example, you could take a paper clip and you could sort of stretch it out, and if you rubbed it across a magnet in the right way, that paper clip can actually become magnetized, and you could take that magnetized paper clip and actually pick up other paper clips. That's a little demonstration that we could do. See if I can find a video on that just to show some examples. You can do the same thing with a nail, though it does have to be a certain type of nail. The nail basically has to contain iron, and it can't be galvanized. A galvanized nail actually doesn't work. You can also have electromagnets. Electromagnets are basically coils of wire that are wrapped around some core, and when you run current through that coil of wire, it produces a magnetic field. It can exert forces on a permanent magnet that's in the vicinity of that coil. The nice thing about electromagnets is that you can just turn off the current that's going through the coil, and the magnetism part of that electromagnet goes away. So an example of an electromagnet that we might see would be something like at a junkyard, where they want to pick up cars and they want to be able to crush the cars. They might use a really large electromagnet to pick up that car, move it, and then they turn off the current, and then it disconnects from the car, and so on. So, as I mentioned earlier, a magnetic field is basically a field that surrounds a permanent magnet. And so it explains the fact that permanent magnets can exert forces on one another at a distance. So we can see that there's a magnetic field present, or we can test for it, by taking a permanent magnet and then putting another magnet nearby and see if that magnet is deflected. And the type of magnet that we put nearby is a compass. And a compass basically just consists of a little tiny magnet that's sitting on top of like a pin of some sort, and so that magnet, that compass needle, let's say, is able to rotate in the presence of another magnet. So let's take a look at a PhET simulation that allows us to look at permanent magnets. Okay, so here is a permanent magnet. I have a north pole and I have a south pole of that magnet, and here I have a compass. That compass needle is essentially just another little tiny magnet. The red side of that compass is the north. The white side over here is the south. And so as I move the compass around, let's say I move the compass over here towards the north end of the permanent magnet, since this is another little magnet, and unlike poles attract, the north and the south are attracted to one another, and so I get a deflection of that compass needle. And as I move it to different locations, the compass needle actually deflects. It's experiencing a force at a distance. Right? So I can keep moving it around to different locations. And by the time I get to the other side, the north end of that compass is now attracted to the south end of the magnet. So this idea of force at a distance tells us that every place surrounding this permanent magnet, there is a field. It's called a magnetic field. And the direction of the magnetic field is the direction that the compass, the north end of the compass needle, actually points. So I'm going to go ahead and I'm going to click on Show Field. And what it does is it places a whole bunch of these little compasses around so that we can see what the direction of the magnetic field is. So it seems to point away from the north end, and then it kind of bends around towards the south end on the top and the bottom. Turns out there's also a magnetic field inside the magnet. So I'm going to show the field, whoops, wrong thing. I'm going to see inside the magnet, and when I look inside the magnet, there's also a pretty constant, uniform, straight magnetic field inside of that magnet as well. So here we have a picture that's similar to the PhET simulation. It has the north and the south pole of the magnet. We have those compass needles, and then we have these lines drawn, and those lines represent the magnetic field that's present. And if I put the compass any place on that line, the compass would basically line up with those magnetic field lines. So this is what the magnetic field looks like for a bar magnet. This is another picture of the same type of a bar magnet. In this particular case, the picture here shows what are called iron filings, little tiny pieces of iron that have been sprinkled over a surface. And those little tiny pieces of iron behave like temporary magnets, and they line up just like the compass would line up. And so again, it shows the magnetic field. So it turns out that all magnetic fields are actually produced by moving electrical charge. So the fact that you have a north and a south pole and that you have a magnetic field inside of that magnet, that's all coming from the movement of electrical charge. And that's part of the connection between electricity and magnetism. So where does this movement of charge come? So magnetism is really coming from the atomic scale of a particular substance. Inside of an atom, you have the nucleus, and you also have the electrons that are orbiting the nucleus. So the magnetism comes from two parts of an atom. It comes from the electrons spinning on their axis. Now the electrons themselves are negatively charged. They are not actually physically spinning about an axis like the Earth spins on its axis. But we say that these electrons have magnetic spin. So these electrons, as they're orbiting the nucleus, actually produce a magnetic field. They behave as little tiny magnets. Also, as the electron orbits the nucleus, that movement of the electric charge also produces what's called a magnetic dipole, or a tiny magnetic field. And so there's two different contributions to magnetism on the atomic scale, the spinning of the electrons and then the electron orbiting the nucleus. In most materials, the electron effects actually cancel each other out because of the spin and which way the spin is, and what the direction of the orbits around the nucleus. So this is one example, but you could also have an electron over here that has an opposite spin, and then those two effects would actually cancel each other out. There are some substances like iron, nickel, cobalt, where the fields or those electron effects don't completely cancel each other out. And those particular types of materials can have strong magnetic effects. And so those are the ones that we're going to sort of focus on, are these materials, these ferromagnetic materials, where those effects from the motion of the electron does not cancel out. But the electrons that are producing these magnets are behaving like little magnets. have what are called magnetic dipoles, which is basically like they're just behaving like a little tiny magnet. So it turns out that all magnets have a north and a south pole. And if you break a magnet in half, you can't separate out the north pole and the south pole. With electricity, you can have a positive charge and you can have a negative charge, and they can be separated from one another. And you can have a positive charge all by itself. You can have a negative charge all by itself. But when it comes to magnets, you can't have just a south pole all by itself or just a north pole all by itself. So there's no single poles. If you take a magnet like this one right here that has a north and a south pole and you somehow break it in half, you end up getting two new magnets with a north and a south pole. So where you broke it, you'll form a new north pole and a new south pole on the opposite pieces of the magnet. So we can sort of ask the question, where do these magnetic poles actually come from? So when we talk about magnetic materials, it turns out that the one that we're going to focus on, where we can actually make permanent magnets, are called ferromagnetic materials. But we also have what are called paramagnetic materials. So with paramagnetic materials, the magnetic dipoles from the electrons as they are spinning on their axis and moving around the nucleus, those magnetic dipoles from those electrons are actually arranged randomly. And so here's an example here of a paramagnetic material, and those arrows, the blue arrows here, just represent the magnetic dipoles of those electrons inside the material that make up the atoms. If you take that paramagnetic material and you place it in a strong external magnetic field, what happens is that those magnetic dipoles, those little tiny magnets, those electrons behaving as magnets, all tend to line up with one another. So here's a picture of that paramagnetic material where those magnetic dipoles, those little tiny magnets from the electrons, are arranged randomly, and then you place it in a strong magnetic field and all of those magnetic dipoles tend to line up. The thing about a paramagnetic material is that once you take away the magnetic field, then this material goes back to behaving like it did before, where those magnetic dipoles are just kind of random all over the place. So it's a temporary magnetism that we see with these paramagnetic materials, and it's not a very strong magnetism. Ferromagnetic materials, on the other hand, have these regions, these clustered regions of aligned magnetic dipoles, and they're called domains. So here is a ferromagnetic material, and there is a big chunk, or there is a small range. This is like looking under a microscope, for example, if we were to imagine what we could do. And we look at a range, and in a certain region, there are these electric dipoles, but they're all lined up. So unlike paramagnetic materials where it's all random, there's these regions called domains where they're all lined up, and then there's another domain nearby where they're all lined up but not in the same direction, and then another domain where they're all lined up, again, not in the same direction, and so on. So normally the domains are jumbled up, right? So they are lined up in the domain, but the domains themselves are just jumbled up in all different directions. But what happens is when you take that ferromagnetic material and you place it in the presence of a magnetic field, all of those domains end up lining up with one another. And they line up with the direction of the external magnetic field. The difference with a ferromagnetic material is once those domains line up, when you take away the magnetic field, the domains don't go back to the way they were before. They keep a little bit of their magnetism because they're all, it's like you have a whole bunch of compasses and they're all lined up, and there's no reason for them to go back now because you had these domains where they were already lined up together. So if we wanted to create a permanent magnet, we could take a piece of iron that is unmagnetized. So that's my picture right here, and here are my my electron magnetic dipoles here, right? These electrons behaving as little tiny magnets, and it's all random. And what I can do is I can take that and I can put it in a magnetic field. So when I put it in a slight magnetic field, or a small magnetic field, that material becomes slightly magnetized. So those domains start to line up in the direction of the magnetic field. And then as I put it in a stronger magnetic field, all those magnetic dipoles tend to line up with one another. So in materials like iron, nickel, cobalt, these ferromagnetic materials, the domains are going to remain after the external field is actually removed. So I put it in a strong magnetic field, it becomes magnetized, and then it basically keeps some of that magnetism. Now, there are some things that you have to do to create a permanent magnet. So you can't just put it in a strong magnetic field. It won't stay to be a permanent magnet. You have to use heat and things like that. But the idea is the same. But once you have these domains all lined up, you can imagine coming over to this magnet here and now breaking it in half. So if you break it in half, you get a picture that looks like these two pictures down here, where you still have all these domains inside these magnetic dipoles that are lined up, where the arrow that points towards the north is the north end, and then the tail of the arrow is the south end. And so I get two new magnets. Because of the fact that those domains are lined up and you're just cutting it, you still have these two regions of lined up domains.